Hello, hi. I think we will start because it's already 7. Okay, good. Right timing. Fine. So, I think we will start then. So, let me share my screen. Okay. Yep. So, screen's visible, I'm audible, video is visible, everything fine, right? Yes, no? Hello.
Yes, ma'am.
Okay, thank you for the confirmation. Yeah, so good evening. And welcome to today's tutorial session on urban utilities planning, water supply, sanitation, and drainage. So this will be the last session for this course. The 12-week course is the 12th week. Probably we'll have one more session for exam preparation that we will have, but for the main course contents, this would be the last session. So today we will look into the contents which we discussed in week 12. So these are the topics which we discussed in topics. Okay, there's some slight lag. Yeah. So these are the topics which we discussed in week 12. So mainly we discussed two aspects, groundwater recharge and flood management, but we went into the details of these aspects by looking into what are the different groundwater recharge measures. And we also looked into different softwares that can be used in order to predict the water flow, the water layout, and flood management techniques and all that. So whatever, most of the things which we discussed in our previous lecture, we saw a practical application about all these aspects in week 12. So the whole this urban water utilities is concluding by looking at the practical applications, and we're looking at the softwares or future prospects on how we can improve our systems further using these softwares and methods which are currently available. So let's get started with the questions. Yeah, so this you know. So let's go to the first question. First one is, which factor or factors affect the suitability of groundwater recharge areas? A, frequency of rainfall events. B, infiltration capacity of soil. C, suitability of aquifer systems for artificial recharge. D, geological formations of the soil. So let's go option by option. A, does frequency of rainfall affect the suitability of artificial groundwater recharge? Yeah, so any guesses? Or you've seen the lecture, so no need to guess, you would be able to answer. Yes, Partha, do you want to take this question up?
Actually, it won't affect, I guess, rainfall events.
Frequency, okay. So we are talking about artificial groundwater recharge. So let's just revise. So this is something which we learned in our first module or second module probably. So yeah, artificial recharge structures we learned in this one also, the different structures, but the groundwater recharge part we learned in our initial module. So the idea is, if you have the soil, whatever surface water is there, it should percolate down, and there would be a layer, and then it should there would be an aquifer, and then through the aquifer it should go and it should recharge. So this is the whole idea that we have. Now artificial methods, what it does is, we create certain embankments or certain structures so that this recharge happens. For instance, if it's a slope terrain, we would cut them into steps. So these are the bench terracing which we learned. Or so that, so in the slope what happens is, whatever rainfall falls, it immediately falls down. So it cannot percolate, it does not stay on the soil to percolate down. So we cut them into terrace so that at least in this portion it stays, then in this portion it stays. So this much percolation happens. So this is for slopes. Now, if it is for other undulated surface, sometimes we even cut these, we use gully plugging, or we create certain uh, structure so that water is stored in that particular region, and then slowly it can percolate down. So these are some of the artificial recharge methods. So mainly now, so this is the factor which happens, and the question asks what are the different factors which contribute towards this, or which affect the suitability, or which acts as a, which influences, it's all the same factors contributing, affecting the suitability, or which influences all these, like what are the different factors which influence artificial groundwater recharge. So first one is frequency of rainfall. So if in this particular case, if there is more rainfall, will the percolation be more or less, or no difference? Okay,
It will be less. It will be less.
if the frequency of rainfall event, okay, frequency of rainfall event is highly frequent, which means there's more frequency, then you're saying that the percolation will be less, or whatever. Let's not look at the percolation, the recharge, the underground water recharge will be more or less. More rain is falling, more is getting percolated. So this would, okay, there might be a saturation limit. So the saturation limit will reach faster, right? If there's more rainfall which happens. Yes, it obviously depends upon the intensity of rainfall also. Here, yeah, so directly we cannot say there's a direct relationship, but there will be some relationship that if the frequency changes, then the amount of water which is there in the aquifer will also change, or the underground water recharge measure will, underground water which is available will also change? Yes, no? Do you agree with me or not? Pata, you there? Uh, s- Hello?
Yes, ma'am.
Yeah,
Yes,
so,
ma'am. But I'm not sure about.
oh, okay. So okay. So simple thing, you have a surface. Now there's heavy rain. So there in a day, there's only one rainfall event. Let's assume same intensity. We are not talking about intensity right now. Same intensity, some amount of rainfall is there. Now this is going to percolate down. Imagine there's no water over here. So I'm assuming 100% percolation, or whatever, because it's the same soil that I'm assuming. If it's 100% percolation, then this intensity I would reach the aquifer right now. Now imagine in the same, under the same circumstances, two rainfall events are happening. So two times intensity, like the frequency, it's getting repeated, like twice the same intensity is happening. So it's coming down, and 100% percolation again. So this will be 2i. So which means the underground water cut, and let's say the 3i is the maximum for this recharge structure, underground recharge structure. It will be saturated when 3i amount of water is there in the aquifer. So then in that case, in this one is I and this one is 2i. So which means as the frequency increased, the amount of rainfall, or the amount of groundwater also changed. Agreed? This much you have agreed?
Yes, ma'am.
Okay. So now the question is asking us which factors affect the suitability of artificial groundwater recharge. So now, if this is a flat land with this 100% percolation, and if this is happening, like with the frequency of rainfall, if this is there, then maybe we don't need to do anything. Now imagine you have a slope land or something where rainwater is immediately flowing off. So if it is more frequent, then more water flows out. But if it is less frequent, then like it, if it is more frequent, probably there is some amount of percolation which is there, because there's continuously water is keeping on flowing. But if the frequency reduces, then it comes and it immediately goes off. So which means the water is not being able to penetrate inside. So which means you will need an artificial recharge structure over there. So that's what the question is asking. Will frequency of rainfall event affect the suitability of artificial groundwater recharge? where we say that yes, it affects, because based on the frequency of rainfall, because frequency of rainfall affects the percolation, affects the underwater recharge. So everything is linked. So this is linked to this. And now our artificial recharge structure, there are many other aspects. Now I'm isolating this aspect and then taking, so this aspect also contribute towards the suitability of artificial groundwater recharge. If the frequency is changing, then the amount of recharge which is there will also change. If it is a place with very less frequent rainfall, then we would need an artificial recharge structure. Like for instance, this one, we would need a structure where water can be stored and water will go down. If it is highly frequent, maybe that water recharge structure is not needed, because within that time itself, it might be able to percolate inside because it's continuously raining. So here, frequency of rainfall affects the suitability of artificial groundwater recharge. Let's go to the next option, B, infiltration capacity of the soil. Does it affect or not? Yes, no?
Yes, ma'am.
Yes, because that's what we were discussing, like infiltration or percolation rate, both essentially the same. So it will influence the suitability of artificial groundwater recharge. Yes. Now C, suitability of aquifer systems for artificial recharge. Yes, no? We've been discussing that.
I think no.
Suitability of aquifer for artificial. So what is an aquifer? So aquifer, so when the water goes down, then where the underground recharge structure is held in this in the aquifer. So aquifer is the surface where the underground water is there. There is a can be a pervious membrane, and then there can be an aquifer below it. So if the aquifer does not allow, or for instance, here we said that the maximum capacity of this one is 3I. So which means the aquifer has a capacity. So if the aquifer does not allow for artificial recharge, for instance, if the capacity of the aquifer is already met with the normal rainfall event itself, then creating an artificial groundwater recharge structure or creating embankments for that will not add any benefit towards it. So we need to see whether the aquifer is suitable or the aquifer is capable of taking this artificial recharged water also. So yes, suitability of aquifer systems for artificial recharge is important. Now, option D, geological formations of the soil. Will that influence?
Yes, ma'am.
Yes,
Yes,
that is
ma'am.
exactly what we were discussing right now. Like, for instance, if you have a slope land or if you have a terrain land, and then talking about the soil type, the percolation rate or the infiltration capacity of the soil. So all these will influence the artificial recharge structure that we will be designing over there. So geological formations of the soil also influences the suitability. So all the four options, like frequency of rainfall event, infiltration capacity, suitability of aquifer systems, and geological formations influence the suitability of artificial groundwater recharge. So this is what we saw in the lecture for suitability of recharge area. We saw that climate influences based on high rainfall or low rainfall. So this is excess rainfall needs to be stored for recharge. Water has to be imported. So if it is excess rainfall, also in certain cases we'll have to store it. So that's why we will need. If it is low rainfall, also water has to be imported from trans-basin area in addition to storage measures of for runoff. So both for high rainfall and low rainfall regions, it would be needed. So frequency affects in both ways. Then you have topography. So this is what we were discussing in the last option, the geological formations. Yes, it influences. Then you have the hydrological conditions, geological formations. So yes, so this is what we discussed. So you may visit this part of the lecture once more to get a more detailed understanding if required. Any doubts in this question? Okay, let's proceed to the next question.
No, ma'am.
Yeah, thank you. So, question two, subsurface water storage capacity of artificial recharge depends on A, water table contours, B, depth to water level during the post-monsoon period, C, suitability of aquifer systems for artificial recharge, D, thickness of unsaturated material above the water table in the unconfined aquifer. Okay, so this is similar to the previous question. So let's see. Aishwarya, can you take this question up? Hello. Is there a time lag? Oh, your mic is not working. Oh, okay, fine. That's totally fine. So, do you want to attempt it in the chat box? Like, which one do you feel is the answer? Where's the chat box? Yeah. Okay, so let's go option by option. A, water table contours. Does this affect subsurface water storage capacity? So the highlight over here is here we are talking about subsurface water storage capacity. The previous question was for underground recharge, artificial measures for underground water recharge. This is subsurface. So, you have surface water, you have underground water, and subsurface water, which is like just below the surface. So, we are talking about subsurface water storage capacity. So, yes, so does it depend on the water table contours? Yes, no, you can type it in the chat box, Aishwarya.
No, ma'am.
Okay, Partha says
No,
no.
ma'am.
Aishwarya? Okay, so Partha says no. Aishwarya also says no. Okay, so let's discuss that a bit. So if we have, so what is essentially water table? So water table is the level to which water is there. So uh, for instance, the underground or the underground water. So if we usually draw a well, then the opening of the well has to touch till the water table so that we can draw it. We also learned about scenarios where when we excessively draw water using a tuber, the water table also bends and it can lead to so bending of water table also, which means in certain regions the water table level will be different. So this is what is water table. So here we are talking about subsurface water storage capacity. Now we know that subsurface is somewhere over here. Let's say that this is the subsurface. And due to some reason, if my water table rises, like because of excessive recharge or something, if my water table is rising up to the subsurface level, then won't the surface storage capacity be altered because of the water table?
Yes, ma'am, it will.
It will be. Oh, very good. Very good. Your mic is working. So in that case, your subsurface storage depends upon your water table contours. If your water, based on where your water table contour lies, your subsurface capacity will also change. How much it can hold will also change. So this influences so water table contours, what subsurface storage capacity depends on the water table contour. So that's a right statement actually. So let's go to the next one. B, depth to water level during the post-monsoon period.
Yes, ma'am.
Yes,
It
that
will.
also influences because it's the same thing. So depth to during the post-monsoon period, what is the depth to the water level? Like where the water level and what is the depth to this water level? That also influences how much of water can be. So based on this depth, that much of water can be stored in the subsurface. So yes, that also influences. Now C, suitability of aquifer systems for artificial recharge. Does that depend?
I don't think.
I'm not sure, ma'am.
Yes, I don't think it will.
You don't think it will. Why
Yes,
do you feel it will not? I mean, there might be something which made you think that it's not, right? So why?
Subsurface water storage capacity is natural occurring, where
for
option C is for artificial recharge.
Okay, okay, fine. Yeah, that's also one point. But again, subsurface also we can use certain artificial methods in order to recharge our subsurface water. So we can't use a blanket term saying that subsurface water storage capacity is only natural because we can use like if we construct some structures over there, we can use that in order to store water in the subsurface soil also. But you're right in one aspect, that here we are talking about artificial, like aquifer systems are mainly for underground storage treatment, artificial or natural, but underground storage, water storage. Here we are talking about subsurface. So the question of aquifer doesn't come over there, because aquifer lies much below where the underground water is stored. Here we are talking about surface, something below the surface, which is a subsurface, but underground is below. So whatever happens below the subsurface, the storage capacity will not depend, right? Because water is coming from the top. So whatever, so after the subsurface, through the subsurface it passes, and only then it will go to the aquifer. So the aquifer doesn't come into picture over here. So yes, so you're partially correct, but maybe I felt that this is what you meant to say, but maybe the term you used was different. So yeah, so absolutely right. Suitability of aquifer systems for artificial recharge is not a factor that influences subsurface water storage capacity. And now the last one, thickness of unsaturated material above the water table in the unconfined aquifer.
Yes, ma'am. It affects the
It affects, yes,
recharge.
yes, because it's the unsaturated material. So if it is an unsaturated material, then the amount that has to be saturated for the water to start coming down. So that thickness, so it's inverse. So what happens? If the thickness increases, will the saturation increase or decrease? Or the time required for saturation will increase or decrease?
It will increase, ma'am.
Increase, yeah. So it's inversely proportional. So if the like for instance, if the saturation, that if there's more thickness, then there would be more, like it will take more time to saturate. So in this case, it will affect the storage capacity also. So yes, so the answer for this is A, B, and D. C is not there, right? Any doubts in this question?
Ma'am, what is meant by that unconfined aquifer?
Oh yeah, so we learned in the previous one, right? So we have confined aquifer and unconfined aquifer. So if you have a pervious layer on top, then it is a confined aquifer. If you don't have a pervious layer on top, then it is an unconfined aquifer. So we can just easily draw from here. But some aquifers, there would be a pervious layer on the top, so which means it's confined. Wait, I might have to check that, confined and unconfined. Just it's there in the lectures. Wait, I'll tell this to you by the end of the class. Let me not give you now. I'm also getting a bit confused right now, which was confined and which was unconfined. So by the end of the class, I'll just check and tell you. Just remind me once,
Okay.
okay? I mean, I'll
Okay.
show you the slide so that it becomes clear.
Unconfined, in unconfined aquifer, like rocks will be there.
Yeah, exactly. So it's the pervious layer which will be there. So if it, sorry, there'll be an impervious layer on top. So that's what it is. But I'll show you the slide so that it becomes clear. So we have discussed this in detail in one of the previous lectures. Okay, so let's go to the next question. Question 3. Identify the correct notation for the volume of water required for artificial recharge. A, volume is equal to volume of subsurface storage into recharge efficiency. B, volume is equal to intercontour areas below cutoff level into specific yield divided by recharge efficiency of the structure. C, volume is equal to intercontour areas below cutoff level into specific yield into recharge efficiency. And D, volume is equal to volume of subsurface storage into specific yield into reciprocal of recharge efficiency. So we have been asked to find the volume of water required for artificial recharge. Yes, so you can attempt this question and then we'll discuss.
And is it option B?
Option B, okay. Volume is equal to intercontour areas below cutoff level into specific yield divided by recharge efficiency of the structure. Okay, Aishwarya, what do you feel is the answer?
Not sure, ma'am.
Okay. So, Partha, do you want to Explain why you feel it's option B.
It was just a guess. I am
Okay, okay.
not
So
having
you're right
technical
at
explanation.
yeah, so you're right. Option B is the correct answer. It is the volume of intercontour
That
areas.
because of that specific yield, it,
Specific yield is there in all the options.
but I felt that one is correct.
Well, your intuition has helped you this time. So, yeah, so this is not a direct question. So, we need to think a bit, like it's a bit tricky question. So, in our lecture, we discussed that. So let's go. So, this is what we saw in the lecture where we discussed about planning for artificial recharge. So, in this, we saw that volume of subsurface storage space, that is how much of space we need to leave for subsurface storage, which is available for our recharge is intercontour areas below a certain cutoff level into specific yield. So this is the contour. So we've discussed like a contour is a region which the same level of water, like it's the what like the water table in that region would be of the same level. So these are the water table contours. So on all these regions, the height of the water table would be the same, and then the remain. So whenever there's a change, you have a separate line over there. So that's why for all the regions with the same water level, we separate it into different regions, and that region into the specific yield of that region. So specific yield means how much can be yielded out from there, or what is the capacity that can be yielded out from there. So that gives us the subsurface storage space available for recharge. Now, once we get, so here we've been asked about the amount of water which is there. So the volume of water which we need. So for volume of water, this amount of space alone might not be adequate. We also need to know what is the recharge efficiency also. So from the first part, we got the volume of subsurface storage available. Now in the second one, this volume of subsurface storage, we're using that and dividing this with the recharge efficiency of the structure. That will give us the water volume of water required for artificial recharge. Now, why this recharge efficiency is important is because sometimes all the water will not go. So even if you have so much of, so if I imagine I have this much volume, but all the water that comes into this, or the amount of water which is needed, so here it's the volume of water which is needed, right? So 100% will never go inside, right? Some will be lost. So that's why we're looking at the efficiency. So based on the efficiency, like if the efficiency is 80 percentage, then we need to account for that. In order to fulfill this, we need to provide that additional 20 percentage of water also, right? Because some amount of water is going to be lost in the process. So we'll have to combine both this and then write volume of water required for artificial recharge will be equal to. So instead of writing this volume of subsurface storage space, we will write this one. Intercontour areas below a certain level, cutoff level, into specific yield, into the reciprocal of recharge efficiency, which is given in which is given in option D. Intercontour areas below cutoff level into the specific yield divided by, so instead of writing reciprocal of recharge efficiency, it's been again written as divided by recharge efficiency of the structure. Any doubts in this question?
No,
Okay,
ma'am.
let's proceed to the next question. Question 4. Which statement or statements are correct among the given statements regarding groundwater recharge? A. Artificial recharge reduces soil erosion, flood, and ensures adequate soil moisture. B. Piezometric surface is lower during artificial recharge of groundwater. C. Artificial recharge can be achieved by artificially changing natural conditions. D. Artificial recharge increases inundation. So let's go option by option. A. Artificial recharge reduces soil erosion, flood, and ensures adequate soil moisture. Is that right? Is that right?
Yes, ma'am.
Yes, it's right. So this is a very basic principle of artificial recharge structures that in addition to artificially recharging the underground aquifers, it also reduces soil erosion because you are building a structure for that, and it controls flood because excess surface runoff would be channelized to the underground, so it reduces flood and also moisturizes the soil in the process. So that's the whole process of, like, when it goes through the soil, the soil get moisturized also. So yes, so this is a correct statement. Now B, piezometric surface is lower during artificial recharge of groundwater. Yes, no?
I think piezometric surface will be constant now. Like just it is adjustable.
It will not be constant, but will it lower during artificial recharge of groundwater? What is piezometric
No,
surface, by the way?
ma'am, like line joining, like if different water levels is there,
Correct.
there will be a line joining
Correct.
thing.
It's an
So that
imaginary
is
line showing the water level, like for different regions, the water levels, like a potentiometric surface. We have a piezometric surface. So it's essentially the based on the water pressure which is there, you have this line joining the. So it's an imaginary line. So now when you're artificially recharging the groundwater, will that surface increase or decrease? Or will the imaginary line go up or go down?
it will go up, ma'am.
It will go up because you're recharging the groundwater, right? So the water level will increase. So this statement is wrong because it's mentioned that piezometric surface is lower during the artificial recharge of groundwater, whereas actually it will be raised, like the piezometric surface would be raised during that time. So this is wrong in that aspect. Now option C, artificial recharge can be achieved by artificially changing natural conditions. Is it correct?
I'm not sure, ma'am.
Okay.
I think we can.
Yes, ma'am.
Yes,
We
it is.
can.
So this is the whole principle of artificial recharge. So what we are doing is we are doing some artificial. So like what we discussed, we like gully plugs or embank. So essentially, we're just creating certain embankments so that water would be stored in this region and it will not just flow off through the surface and it will percolate down. So the whole principle is that artificial recharge can be achieved by artificially we are changing the natural conditions and we are doing this. Apart from that, we are not doing anything else. So this is the basic definition itself. Now, option D, artificial recharge increases inundation. Yes, no?
False, ma'am.
Okay, what is the correct statement?
It
Reduce.
decreases.
Reduce.
Yes, it reduces inundation. Correct. So so it reduces soil erosion, flood, and ensures adequate soil moisture. So it's the exact opposite what is given over here, right? Artificial recharge increases inundation. No, it reduces inundation. So in that, so what should we mark? We have to mark the correct answer. So A and C are correct. So option C, A and C. Any doubts in this question? No. Okay, let's proceed to the next. Yeah, so this is
No,
what
no.
we discussed. So yeah, so the hydraulic effects are generated by artificial recharge and the piezometric. So there's a piezometric effect which leads to the rise of the piezometric surface. So this is what we discussed in the previous question. And yes, what is artificial recharge? This is achieved by artificially changing the natural contours. Sorry, natural conditions. And in the benefits of artificial recharge, we have seen that it reduces inundation. Other benefits like it improves water quality, reduces soil. Yeah, this also reduces soil erosion, flood, and ensures adequate soil moisture even in summers. So these were all the options. So let's go to the next question. Question 5. Match the following and mark the option for the correct match. So P is ditch and for. So these are different terms, and what is the artificial groundwater technique that we're using is the options to which we are to mark this to. So we have ditch and furrows, gully plugs, gravity head recharge, sorry, bore blasting. So let's see the first one, ditch and furrow. Which of the following does it correctly come? Is it an aquifer modification? Is it a subsurface technique? Is it a surface spreading technique? Or is it a runoff conservation technique?
Subsurface.
Ditch and furrow is a. So what is ditch and furrow? So like so we have something like this, right? So you have a ditch and then you have a furrow. Like in the irrigation also we learned something similar. So this is again done so that water would stay over here and it would go down. This is the artificial method. So what are we modifying over here? Are we modifying the aquifer, subsurface, surface or runoff?
Surface spreading technique.
So this is a surface spreading technique because we are modifying the surface over here. It's not a subsurface because you're not going into the subsurface in this case. Then, okay, so it correct, very, very good. It's a surface spreading technique. Now, what is gully plug? Okay, what is gully plug? What do we do there? So if we have, so in this, let's take this itself. So imagine we have a gully like this. So it's a normal gully. So in this gully, we are plugging it with some rocks or something. So we are creating something like this so that whatever water falls over here will be stayed. So these are the plugs that we use. So this region becomes a gully plug. So in that also, yeah. So what is that essentially? Is it a surface spreading technique? So surface is already gone. So are we modifying the aquifer? Definitely not. Is it a subsurface? No, we are not going into the subsurface. So we are left with runoff conservation method. So yes, so that's what we are doing. We are not allowed. So by creating plugs on either sides, we are not allowing the surface runoff to keep going. So that runoff, we are collecting it and we are channelizing it so that it will go down. So it's a runoff conservation structure. Now R, gravity head recharge wells.
Subsurface techniques.
Gravity head recharge wells is a subsurface technique. Very good. So because why? Because it's a gravity head recharge well. So you have these wells through which it just goes and it just recharges the subsurface. So it's a subsurface. Very good. It's a subsurface technique. Now last one, bore blasting. Yeah, so that's the option, aquifer modification.
Aquifer.
Yeah, that's the only
Aquifer.
option we are left with. But what happens is, so you have these bores. So now, imagine this is the aquifer. Now, it might be a pervious, like that might be small aquifers. Now, when you blast this, when you use a bore blasting and when you blast the aquifers or the permeous membranes in the aquifer, the entire aquifer may combine to become one aquifer. All the impervious rocks which were there would have been blasted. So you're modifying the whole aquifer profile so that more groundwater recharge can happen or it can hold more groundwater. So bore blasting is an aquifer modification method. So this is what we saw in the lecture. So yeah, no, this is not from the lecture. This have added something additional. So yeah, so you have a ridge and you have a furrow. So this is what we were discussing. So this is a surface method, and then you have these gully plugs which becomes you're trying to contain the rainwater, so it becomes a runoff conservation method. And this is the gravity well, so it becomes a subsurface. So this is for the subsurface method, and this is aquifer. So you see, this was a natural channel before. Now when you blast these, when you do a bore blast, then the channel also changes. So you're modifying the aquifer using bore blast. This is what we saw in the lecture in the different artificial recharge methods. So for aquifer modification, we use bore blasting, hydrofracturing, which mostly for increasing the yield. So this is so bore blasting is to increase the connection, whereas hydrofracturing can be used in order to increase the yield from the well. And the other ones, where are they? Yeah, surface spreading techniques. We have ditch and furrow technique, which is what we discussed, and then we also have these runoff conservation techniques, which is gully plugs, nullas, check dams, and all that. Okay, so let's go to the next question. Is there any doubts in this question? No. Okay, let's go to the next question. Question 6. Which statement or statements are incorrect about recharge basins? A. These are suitable for lands joining rivers or canals with sufficient non-committed water. B. They should have a gentle slope with diagonally placed entry and exit points. C. They should be constructed perpendicular to intermittent streams. D. Rate of inflow into the recharge basin should be less than the infiltration capacity of the basin. So let's go option by option. Option A, these are suitable for lands joining rivers or canals with sufficient non-committed water. Is that a correct statement? Is that a correct statement? Anything, attempt, any guesses? No guesses also.
No, no, no.
Okay, this is a very
You
okay.
have to go the
Not
incorrect
necessary.
statement, Roma.
It,
Huh?
it is not necessary that it should be.
It is not necessary, I agreed. It is not necessary that it should be built next to rivers or canals, but yeah, the statement doesn't say that it should be built, right? So let's see that way. The statement just says that these are suitable for lands adjoining rivers or canals with sufficient non-committed water. So are they suitable? Like, can we build it over there?
Yes, ma'am.
Yes, so it can. And why is it suitable? Because you have an adjacent river or canal, so you can easily get the water out of it. And this is surface water. And we need to recharge the underground water. So you can make use of the surface water easily in order to recharge the underground water. But one catch is that it should be sufficient non-committed water. What do we mean by non-committed water? Non-committed water. So water, usually from the rivers and all, we have this um, we have water is usually assigned for particular tasks. Like for instance, water from this particular river will be sent, will be purified and then sent to the residential buildings in this particular region, or it will be sent to this industry. So usually water is committed in that way, like you're assigning the water to a certain use. So whatever water has been assigned for a particular use, we cannot use that in order to recharge our underground underground reservoirs. So that is why it said that if you have sufficient non-committed water, which means water which is not being used for anything, then these are suitable for recharging the basins in the adjacent, suitable for recharging adjacent basins. So yeah, so this is a correct statement. Now option B, they should have gentle slope with diagonally placed entry and exit points. Is that a requirement? Should they have a gentle slope with diagonally placed entry and exit points?
Yes, ma'am.
Yes. Why? Because you want the water to be there in that particular region, right? So you need to have a diagonal slope so that the surface water comes and then, so this is a basin. This is an artificial recharge basin that would be creating. So it should have these entry and maybe it would have an exit point, something like this again, so that it exits and it goes down. So it should have these diagonally placed entry and exit points. Okay, so that's also a correct statement. Now then you have option C. They should be constructed perpendicular to intermittent streams. Is that correct?
No, no, it should be parallel.
It should be parallel. Very good. Why should it be parallel? Why should it be parallel?
And if it is perpendicular, it may affect the stream.
Very good. Yes. If it's perpendicular, then you're obstructing the stream. So your idea is that there is a stream, you construct something here, so parallelly you divert the channel a bit and then you recharge over here. But if you construct something perpendicular like this, perpendicular like this, then you're actually obstructing the stream. So it will, water will not flow after that, right? So you don't want that to happen. So they usually constructed parallel. So this is a wrong statement. They are constructed parallel to the intermittent streams. Then D, rate of flow into the recharge basin should be less than the infiltration capacity of the basin. Is that a correct statement? This is a very
I
logical
think it
question.
will
You
be
can,
more.
yes, very good.
It will be
It
more.
should be more because if it is less, then you will not have adequate water to infiltrate down, right? Whatever comes, immediately it infiltrates down. So the rate of inflow should be slightly greater than the infiltration capacity so that there's always some amount of water and there's always some amount of infiltration happening. So that only when it reaches saturation, the infiltration would stop. Otherwise, even before it reaches saturation, like for some time infiltration will not be there because there's no water to infiltrate. So this is a wrong statement. So here we have been asked to mark the incorrect statement. So C and D are incorrect. So option D is the answer. Any doubts in this particular question? So this is what we
No,
saw
ma'am.
in the, yeah, you have a doubt?
I said no, ma'am.
Oh,
No,
okay, sorry.
no.
Yeah. So this is what we saw in the lecture of why we need this. Yeah. So this is the stream that we have. So parallel to that, we are constructing the recharge basin. We also need certain slopes for the entry and exit points, so that from one entry, so this is slope this way, so it enters, then it's slope this way, so it goes. Now here it's slope this way, then it's slope. So for entry and exit, the slope is given properly so that it enters one and then easily exit to the other one. So what else was there in the option? Constructed perpendicular, gentle slope, suitable for adjacent. Yeah, so we have discussed all the aspects over here. Question 7. Match the following and mark the option for the correct match. So we have different methods in the different terms of the methods and their descriptions on the right hand side. So let's go by each term. Contour beds. So we have contour beds, percolation tanks, injection wells, and recharge pits. So all these are different recharge structures that we are using. So first, contour beds, are they can they recharge multiple? Okay, for options, can recharge multiple aquifers, recharge wire infiltrating through the Vado zone. Three, embankments of land along contours in low rainfall areas, and four, surface water bodies created over highly permeable area. So which is contour bed? Sorry, contour bunt. Sorry, contour bunt. So it's a bunt. Essentially, it's a bunt means something which you where you
It's
block.
embankment.
Very good. Yeah, it's an embankment.
Embankment
So it's
3.
the contour bunts is an embankments of land along contours uh in low rainfall areas. So it's something like that. Like you in low rainfall areas, we construct certain bunts like this so that in each based on the contours. So if you have a contoured land, so based on the contours, you construct these bunds so that water will not easily flow out. Like if it's a contour like this, we construct these bunds so that water won't easily flow out and it will be there. So embankments of land along contours in low rainfall areas. Correct. Now Q, percolation tanks.
Surface body water created over a highly permeable area.
Yeah, so the whole idea is it should percolate. So that is there in this question, that it's built over a highly permeable area. So these are surface water bodies created over a highly permeable area so that maximum percolation happens. So very good. Yes, correct. Now our injection wells.
Recharge via infiltrating through
Vado.
Vado zone.
That is injection well. Okay. So what is recharge pit then? Can a recharge pit recharge multiple aquifers? Think. So
Okay, I
we have
think I'm
two
wrong.
options. We have two options left. So using those two options, we
Yes, ma'am.
can,
It is
yeah.
RS1.
So now that we have eliminated the other option, here it becomes a bit easy to say that a recharge pit cannot recharge multiple aquifers because a recharge pit is just a small pit. So it recharges that particular aquifer. But if it's an injection well, you're going down. So into the aquifer. So there can be multiple aquifers over there. So you can recharge multiple aquifers. So an injection well can recharge multiple aquifers. And because the recharge pit can't, we can easily go into this and say that recharge pit recharges via infiltrating to the Vado zone. And also, yes, so recharge pit, it's a pit, right? So it infiltrates through the Vado zone and it goes down. So that's what. But injection well is injected. So it's no infiltration happens in the Vado zone. Everything is injected down and directly it's going into the aquifer. So this is the answer. So it is P3Q4 R1 and S2. Q4 are option C, right? P3, Q4, R1 and S. Yeah. So, okay. Yeah, so that I thought I had some material. Yeah. So, yeah, so this is so let me just sketch it out for you. So if you have an injection well, so it's a deep well that we have, right? So you can have multiple aquifers which are going. So using this injection well, you can channelize it and you can recharge multiple aquifers using an injection valve. But a recharge pit is a surface structure, so you create something like this. So whatever percolates, it percolates into this particular aquifer which is there. So it recharges and also it infiltrates to the Vado zone and then it goes. So it recharges. So yeah, it is possible that if certain cases there are multiple aquifers which are being joined over here, maybe it's possible. But looking at the two options, injection well is mainly used to recharge multiple aquifers, and it's a recharge pit where you infiltrate through the Vado zone and then goes into one aquifer. So option C is the answer. Any doubts in this question?
No, ma'am.
Okay, let's proceed to the next question. So this is a small problem. It's a very simple problem, not as complex as what we have done before. So let's solve it together. The average monthly volume of rainfall in an area is 100 millimeters. So this again, keep a note of this. Rainfall is always measured in height in millimeters, whereas we might usually people go wrong thinking that rainfall is measured in volume, but that mistake should not happen. Rainfall is always measured in height. So the average monthly rainfall volume of an area is 100 millimeters. The rain water is being collected in a building roof having an area of 250 square meters and the household size of 5. So there are 5 people in the house. Determine the number of days the collected rainwater is adequate for the building. Consider average daily water demand as 120 LPCD if the entire water can be treated and stored without loss. So which means how much of rain, if 120 liters per capita per day is required, for how many days will this 250 will the rainwater harvested through this 250 square meter rooftop last? Essentially that is a question. So let's take what is the information which is given. So we have the average monthly rainfall which is 100 millimeters, which I'm converting into meter, millimeters. So this is monthly. So I'll just make it yearly and then convert. So yearly it will be 100 into 12 millimeters. Converting it into meters, it would be 1.2 meters. Okay. Now, how much of area do we have? So the roof area is equal to 250 square meters. So if that is the case, the amount of rainfall that will be collected in a year, rainfall collected in a year would be 250 into 1.2. How much is that?
Ma'am, 300.
300. 300 what? 300. What is the unit?
With 300 meter
So this
cube.
is
Meter
meter.
cube. Ma'am.
Yeah, correct. Meter cube. So
Meter
this is
cube.
meter. This is meter square. Like area is in meter square. This is the height in meters. So this is the volume. So this is volume. Essentially, what you're getting is a volume of rainfall collected in a year. So here we are talking about the whole, how much of volume or liters that we are collecting. Rainfall, whenever we are measuring rainfall, we always, or the unit of rainfall measurement is in meters. But now we obviously we need to see the capacity or the volume of water that we are taking. So that is measured in meter cube. So this is meter cube. Now this one is given in liters per capita per day. So let's convert it to the meters, the liters. So 1 meter cube is equal to 1,000 liters. That's the conversion. So this one will be 300 into 1,000, so 3 lakh liters. Yeah, so it will be 3 lakh liters, correct. Now our daily consumption is 120 LPCD. LPCD means liters per capita per day. So per capita. So we have per capita, and we know that there are 5 people. So which means daily for every person, like for these 5 people, what will be the consumption daily for 5 people? It would be 120 into 5. How much does that come out to?
600.
It's 600. Ma'am.
600. Yeah, very good. So we need 600 liters. So it is liters per cap. So liters per day. So we need 600 liters in one day. And for the entire year, we are harvesting 3 lakh liters. So for how many days would it last? So it's just so it will be essentially 600 divided by 3 lakh. Sorry, the other way. You have 3 lakh. So I'm just writing it here. So you have 3 lakh, which is the total. And for each day, you need 600. So how many days it's going to last now? 3 lakh divided by 600.
500.
It is 500 days.
500 days. Very good. So it will last for 500. Is that there in the option? Option C, 500 days. Okay. Any doubts in this question? No doubts. Okay. Very good. Let's proceed further. Question 9. Match the following and mark the option for correct match. So different the terms given for different flooding types are given, and what is the description we need to match. So P, fluvial flooding. So we have pluvial and coastal flooding. And the options are occurs due to storm surge, occurs when a rainfall event creates a flood, not related to an overflowing water body, occurs when a river overflows its banks. So yes, let's go to P. Fluvial flooding. What is fluvial flooding?
3, ma'am.
Occurs when a river overflows its banks. Very good. That is fluvial. Correct. Now, what is pluvial flooding if that is the case?
Option 2, ma'am.
Option 2 occurs when rainfall event creates a flood not related to an overflowing water body. So fluvial and pluvial, it's like what is not fluvial, it's pluvial. So that one. And coastal flooding occurs due to storm surge. So I think coastal is easy to remember because it's storm surge. Like whenever there's a storm and then there's a surge, or from the coastal bodies, whenever water level increases, you have coastal flooding. Fluvial and pluvial might get a bit confusing. So one trick that I usually used to remember is that this is fluvial, which means something is flowing. So the river water is overflowing. So because of the overflow, there is a fluvial flooding, and there is a pluvial flooding when it's not related to any overflow mechanism. It's just that there is it's not an overflow from a water body due to some other reason. It is being flooded. So I don't know. Some we need to keep something like this so that we don't forget easily. So let's go to the next question. Let's go to the next. Yeah, so this is what fluvial flooding fluvial. So this is there in the lecture. You can see that. Question 10. Which statement or statements are correct among the given statements? A. Stormwater surge occurs when high winds push seawater to the coast. B. Overland flow and channel flow can converge to nearby streams during fluvial flooding. C. Increase in pervious areas has increased the incidence of floods. D. For 1D approach of flood modeling, surface flows are modeled as open channels or ponds and solved using 1D Saint Venant equations. So let's go option by option. A. Storm surge occurs when high wind pushes seawater to the coast. Is that correct?
Yes, ma'am.
Yes, it's correct. So we just discussed before. That is the correct statement. Now, B. Overland flow and channel flow can converge to nearby streams during fluvial flooding. Is that correct?
Yes.
That's
No, it
correct.
will be pluvial.
Okay. So you're
No,
saying
it's
that's a
not pluvial flooding.
Okay, during pluvial flooding it can be, but during fluvial flooding it's not possible.
I think so.
Yeah, just say it with confidence if you feel that. Yeah, you can't. Because why? Because this is fluvial flooding, which means the river itself is overflowing. So if the river or the streams are overflowing, then it cannot accommodate more water, right? So whatever overflow is there, it cannot converge to the nearby streams because it's already that is the one which is causing the flooding. You're absolutely right. If it was pluvial flooding, then this statement would have been a correct statement. But since it's fluvial, it is a wrong statement. Now see, increase in pervious areas has increased the incidence of flood. Is that a correct statement?
No.
No, it's not a correct statement because if you have more pervious areas, then whatever percolate down, right? Here, water is because it's impervious, water is not percolating down, and that is what causes surface water to increase the surface water and lead to floods. So this is a wrong statement. So D, for 1D approach of flood modeling, surface flows are modeled as open channels or ponds and solved using 1D Saint Venant equations. Is that correct? This is a bit
Yes, ma'am.
detailed. Okay, so Aishwarya says it's not correct. So what is it modeled as if it's not
True,
same
ma'am.
Venant equation?
I said it's true, ma'am.
Oh, you said it's true. Okay, sorry.
It's
Yeah. Okay, so yeah, it is a correct answer. It is 1D Saint Venant equation that we're using. So here, correct answer is A and D. So option C is the answer. So if it was 2D, which is the equation that we would be using? If it is a 2D approach, so let's see. So if for 2D, we use shallow water equations, and for 1D, we go for Saint Venant equation. So this you can remember. If it is 2D, we use shallow water, and 1D Saint Venant equations. Then is there anything else? Yeah, no, that's all. The others were easy. Okay. So let's go to the next question. Question level. HEC RAS is used for sewage treatment simulation, water quality modeling in streams, simulation of ultrafiltration and reverse osmosis, floodplain mapping. Yeah, so I think you can attempt this question. There's no point in going option by option here. What is HEC RAS used for? Any guesses? No guesses. Okay, I can give you a hint.
Floodplain management.
Floodplain management. Yes, very good. Floodplain management. Is only floodplain management? Anything
Wa-
else? Sorry,
water
Aishwarya.
quality.
Water
Water
quality
quality.
modeling. Yes, very good. So as a team, you've solved it very correctly. So you can otherwise, like if you're very clueless about such questions, and at least for this particular week, it would have worked by looking at the fact that we've only discussed artificial groundwater methods and flood mapping. So in that case, we are mainly looking only at floodplain mapping and also some water quality modeling in streams. That's all. Sewage treatment part and again ultra purification part we have not seen in this week's lecture itself. I mean that's if you've not seen the lectures at all, that or I don't know, just roughly
Those
saw
are
the
treatment.
yeah.
Those are treatment
Yeah,
process.
exactly. So these are treatments. So this doesn't come under the purview of this week's content. But apart from that, that's a very crude approach of doing this. But apart from that, so this is a software which we use in order to map floodplains. It also has an additional feature which allows us to look at the water quality. But again, we cannot purify the water, but what is the water quality in the stream that we can see. So option A and C are where there's no. Okay, this is used for B and D. We have been asked to mark the correct statements. Yeah, option D, B and D is the correct statement. So let's just look at that software a bit. So this is the HEC software which is used. So it's yeah, so it is used for flood damage computation, like mainly for flood plain mapping. That's the main idea. And sorry, it is also used to give water quality. Is it there in this one? Processing, digital center line simulation analysis, floodplain mapping, ecosystems, storage, transportation, water geometry, river. Okay, so it's yeah, water quality modeling. It's also used for water quality modeling. So these are the two options which were there in our question. Okay, let's go to the next question. Question 12. Match the following and mark the option for the correct match. So the different drainage systems are given and few examples are given on the right hand side. So first one, P, source control. So it's source control measure, site control measure, and regional control measure. So based on the granularity of control, we need to give which example suits the best. So we have retention pond, infiltration trench, and green roof. So let's do the right hand side and match it to the left hand side. So retention pond, is it a source control measure, site control measure, or a regional control measure?
Regional.
Regional control measure, very good. Because if you have an entire region and if you have a retention pond over here, water from all the region can flow into this retention pond. So it's a regional control measure. Very good. So regional control measure. Infiltration trench. Is it a source control measure or a site control measure?
Site, ma'am.
It's a site control measure. Very good. Because where it's being so infiltration trench means it has to infiltrate. So on the site you're controlling it where the infiltration is happening. So it's not in the source. It's not where water is being generated or water is being collected, but it's where the water is being recharged or how it goes. So the site where water is infiltrating down. So very good. It's a site control measure. Then we have green roof, which is a source control measure because it's on the directly. So it's a source where so rainwater falls on the roof. So that's the source of the water. From the roof, we are getting the water for other purposes. So in the source itself, we are using it for by creating a green roof, we are using it in the source itself on the roof. So it's a source control measure. Very good. So that works out to which option? P is 3 and Q is 2 and R is 1. Option A. Okay. Let's proceed to the next question. Question 13. In flood modeling using HEC-RAS, Delaunay triangulation technique is used to create which of the following? A. 2D computational mesh. B. Terrain model. C. Road network. D. Boundary polygon for flow areas. Delaunay triangulation technique. I know this is a bit technical, so you can just make a wild guess if you don't know.
Terrain model.
Terrain model. Okay. So terrain, no, the answer is for this one you
Boundary
use
polygon.
what?
Boundary polygon.
Boundary
Population.
polygons. Okay, so I understand where you're coming from, Aishwarya. It's actually the 2D computational mesh, which also becomes the boundary polygon for flow area because this mesh becomes the polygon, but we call it the meshing. So it is the so for the entire region we divide it into certain. So it can be a hexagonal mesh or a tetrahedral mesh. So it's essentially a mesh, and this also becomes a boundary. For instance, we see from here where does the water flow? To this direction. How much does it flow? Will it flow to this direction? How much does it flow? So from here, whatever, how is the water flowing? So that network is created based on this 2D computational mesh. So now why it's a computational mesh? Because this is an imaginary mesh which is created for in the computational domain only. So for computational purposes. Whereas when you talk about the boundary of the flow areas, which means that the flow is being restricted over there. So the term we used over here is a 2D computational mesh. Maybe you intended this only, but this is the correct term we use. It's a 2D computational mesh that we are using. So yeah, so this is what is there. So yeah, so we have a boundary polygon which is drawn. So this is the first one. We have the initial boundary polygon, what you were talking about. Then this particular method, the Delaunay triangulation, is used to create the computational mesh. So just to say, this becomes our boundary polygon, and then you have a computational mesh inside this in order to see within the boundary polygon how is the water flow. So the Delaunay triangulation method is to split this boundary polygon into the computational mesh to allow to understand the flow. Okay, so let's proceed. Any doubts in this question?
Hmm.
Okay.
No, ma'am. No, ma'am.
So continuation to that, in question 14, data used in 1D, 2D dual drainage approach using HES, HMS are. So what all data do we need is the question. So do we need land, so A, land use and land cover data, B, hydrological soil group data, C, location of elevated reservoir data, and D, infiltration data. So let's, first one, is land use and land cover data required?
Yes, ma'am.
Yes, land use and land cover data is required because in order to plan the storm water, in order to see how water is flowing, we need to know what is the land cover so that we know that what will be the infiltration rate or the infiltration capacity. We also need to know the land use to know what will be the usage pattern in that region. So we'll have the water flowing. So land use and land cover data are important. Hydrological soil group, is that important? Yes, hydrological soil group is also important
Yes, ma'am.
because, again, for the same reasons, for infiltration, percolation, perviousness, everything, the hydrological soil group matters. Now, see, location of elevated reservoir.
No, I think.
No? I couldn't hear you. Did you say no?
Yes, ma'am.
Okay. Yeah. So location of reservoir is not important because uh, elevated reservoir is a water supply technique or is used in water supply systems. Here we are talking about drainage systems. So we don't, irrespective of where the reservoir is, the drainage system will not change. So it does not matter. So location of elevated reservoir is not a factor. Now D, infiltration.
Yes, ma'am.
Yes, infiltration for all the reasons which we've been discussing uh, from beginning. So yes, infiltration is important. So that works out to A, B, and D. C is not there. Yeah, so this is the 1D, 2D dual drainage approach where we saw the data. So we need the hydrological soil group, curve number, infiltration rate, and time of concentration. So we also need land cover and land use data also, which I think somewhere else, maybe in the previous slide, it was mentioned. For all the drainage approach, land use and land cover data is also needed. Okay. Let's proceed to the next question. Question 15. In which format the digital terrain model of river system is used as input in 1D, 2D dual drainage approach using HES GeoRAS? So this is the software which we have seen. So the digital terrain model, so DTM, digital terrain model, what is the format in which we will use a digital? Is it an SED file, DEM file, ArcInfoTech file, or .bco file? You can guess. Anything, any wild guesses? Is there any, so anything which you know, which you have used in any other software or something? All or new?
I think DEM is related to surveying.
Yeah, it's related. So what is DEM?
I think total station. Not sure about the
Yeah,
instrument.
so DEM is digital elevation model. So it is, you're correct. It is used in surveyors also. While surveying a land, we use that in order to know the elevation or the height of each land. If that's a contoured land, to get the height. So with G in, so this is usually modeled using GIS, where in GIS we take the digital elevation or how much height each region is there. We create a digital elevation model. Here also in using this dual drainage approach also, we use a DEM, but again DEM is not used for terrain. So here we cannot get the terrain information using the elevation model. So that's not what is used over here. So the answer here is ArcInfoTech. This is what we use in order to get the terrain. So it's the formats that we follow. So let's see some other formats which we learned. So yeah, so the digital terrain model DTM in the ArcInfoTech format is used as the input. The other ones like for GIS, we will have the digital elevation model while we are doing the GIS analysis, which is I don't think it's given in this one. So yeah, it's not given. So yeah, so the answer to this question is ArcInfoTech format. I know this is a bit too technical, but there was a question, so we have to answer that. Okay, let's go to the next question. Question 16. In hilly areas, artificial groundwater recharge can be achieved by A. Injection wells, B. Contour bunding, C. Bench terracing, D. Recharge basins. So this you should be able to answer based on the discussion that we have had today. We've been discussing a lot today. So yes, so A. Injection well. Can injection wells be used for recharging groundwater in hilly regions? Or is it needed?
No, ma'am.
No, injection well is used for modifying the aquifers or for underground recharge and other where there's a pervious layer, impervious layer or to modify the aquifer and all that. So it's not injection well. Contour bunding, can that be used?
Yes, ma'am.
Contour bunding can be
Recharge basins can be
recharge basins
used.
can be used in hilly regions.
The bench terracing and
Bench
contour.
terracing and contour benching. Yes, so you have a hilly region. This is bench terracing. Contour bunding also we learnt. In a contour, we create certain bunds. So bench terracing is you cut it out. And in bunting, you create certain bunds or you create certain structures and then you create those bunds. So it's contour bunting and bench terracing. Recharge basin is just a basin, right? You have a basin like that. So you cannot use it in hilly region. So in a hilly region, you create a basin. Again, yes, some water might be there, but it will still keep going out, right? So it's not the popular method that we usually use. It's contour bending and bench terracing. So it is B and C. Let's go to the next question. Question 17. Dash approach of stormwater management manages runoff at the source through distributed, decentralized micro-scale controls. So we have, it's a stormwater management method which manages surface runoff at the source itself by distributed, decentralized micro-scale controls. So this is important. Sorry, we're looking at micro-scale control. So is it water sensitive urban design?
That is not for micro, ma'am.
Yeah, it's for macro. So it's an entire urban design that we are doing, and here we are not designing anything. So we learned about water sensitivity and all in our previous modules. So this is not a distributed, decentralized micro scale control. So no. Then B, is it low impact development?
Yes, ma'am, because it is mentioned as low and it micro, so it will be low impact
Yes,
development.
it is micro. Plus, you are doing it at the source itself. So these are the two keywords you have. We have to do it's a micro scale plus it's done at the source. So low impact development means though that's a source, right, which contributes. So in because of the development, whatever you're developing, it's a low impact development so that you can manage the stormwater better. Like you don't create artificially complete concrete surfaces and then create flooding. Like so that whatever simple small developments that you're doing, that itself you're doing in a very conscious way so that water management becomes efficient later. So yes, so it is low impact development. Let's discuss the others also. The sustainable urban drainage system, that is also not the answer. Why? Because this is an urban drainage system. It's a macro scale system that we're talking about, the entire urban drainage system. Whereas here we have mentioned that it's a micro scale. So this also cannot be the answer. So yes, so it's low impact development. Any doubts in this particular question? No. Okay, let's proceed further. Question 18. Underground bandharas are a type of A, rooftop rainwater collection system, B, subsurface groundwater recharge technique, and C, surface groundwater recharge technique, and D, groundwater conservation technique. Underground. So you have underground bandharas. So first option will definitely go.
Subsurface, ma'am.
What is the answer?
Subsurface groundwater technique.
Subsurface groundwater recharge technique. Okay. Okay, so let's say that these two are gone. Surface groundwater recharge technique and rooftop, these are gone. It's not a subsurface ground, so it's underground. So it's an
I'm sorry,
underground
ma'am. It's
bandara.
groundwater.
It's correct. It's a
Sorry, ma'am. It's ground.
groundwater conservation technique. So the idea is that by creating a bandara, we are saying that water will percolate down and it will recharge the underground water. So it's an underground water conservation technique. Okay. Any doubts in this question? No? Okay, so I think that was the last
No,
question. Yeah, so I just have some explanation. Yeah, so these are intended to retain groundwater for long periods in the basin by arresting the subsurface flow. So partially, yeah, so you're taking the subsurface flow and then you're recharging the underground water. So it's an underground water conservation method. So yeah, so that's it for this week's and essentially for whole of this 12-week courses live session. So if you have any doubts for any of the content for all these 12 weeks, you can ask right now. I will get back to that Aishwarya's unconfined aquifer question. Let me just stop sharing this and I'll share my system and show that slide. One sec. How do I stop sharing this? Stop sharing. Yeah. So if you have any doubts, you can ask them now. Meanwhile, I will just take that. was in the lecture on underground water. So let me just find that. Measurement of rainfall. No. Hmm. Yeah. So let me just share the screen. Where is this? Share the screen. Window. Yeah. Okay. So this is what we learned in our if my screen is visible, right? Yeah. So this is an unconfined. So if you see this gray one, that is a permeable, impermeable cover that we have. So if you have a permeable, impermeable cover, which means you cannot penetrate to it, then it's called a confined aquifer. So you need to dig through that and then go into the aquifer in order to get. So you need to dig through the impermeable cover. Whereas in an unconfined aquifer, you don't have that layer. So it's so you just have to dig probably a bit less so that you don't have to dig through the permeable cover. So is that clear? What is an unconfined and confined aquifer?
Yes, ma'am. Yes, ma'am.
Okay, fine. Fine. So if you have no doubts, so regarding the live session for this one exam preparation or an extra session. So I have given the date as tomorrow is 17th. So I've given it as 18th because I thought of giving you more time to prepare for your exam so that after the live session you can again prepare. So tomorrow we'll have a break and 18th we'll have the live session at this time, same 7 to 9 itself. Is that okay?
Yes, ma'am.
Yes,
Okay,
ma'am.
right. Yeah, you'll be available. No, okay. So yeah. So mostly you will be getting an email regarding or in the course announcement itself, they would be putting that mostly. Uh, I have not. I mean, usually when I inquired, they said that it will be announced to you, so it will be there. If nothing is announced, then I don't know. Maybe then the session won't be there. So look out for the announcement. If the announcement is there, then we will. But this will be the date. This is the date which I've filled out for that. Yeah, so for that session, I was thinking of looking into some numericals. Is there anything else in particular which you would want me to discuss, like anywhere where you have some confusion or something?
As of now, no, ma'am. Maybe if I refer, we may get.
So if you refer and if you feel something is there, then you can put it in the discussion forum by probably by tomorrow or something. If you put then if I come across it, then I will. I mean, if you put in the discussion forum, obviously I'll get a notification, so I'll see that and I'll come prepared with that. Or else I'll have a set of questions. Like it will be the numericals which you have or the type of numericals which you have discussed in class itself, and some of the assignment questions also which you have already submitted and you already have the solution. Even though you have the solution, we'll just solve it once more so that the method is again clear to you. So yeah, so we'll do that then. It's a 2 hour session that I'm planning. If it gets over like this early, then we will leave half an hour early. Okay, so if that's the case, then bye for now. See you both day after tomorrow for that extra session. I hope the session would be there. Just look out for the announcement because since the announcement has not come till now, I'm also a bit confused. But they said that an announcement would be put and link also mostly it will be this link itself. So I think I can switch this on a different day. I feel we'll see that. I think the NPTEL team will sort that. Okay, so have a good night and thank you all for joining.
Thank you, ma'am.
Thank you, ma'am.
Good
Thank you
night.
so much.